All right, these are the solutions to the first energy is not conserved problem set. And I love this question because it's kind of cool to think about, like a real problem. But I wish they'd put a picture with it. So the softball pitcher is swinging, if you can imagine, the wind up, swinging her arms around from A to B, pretend like A and B are a perfect semicircle. The ball has a certain mass, a quarter of a kilogram, and it's going around a vertical circular path of a radius 0.6 because we want to be in meters before releasing it. Boom. So again, this is a person winding up the pitch and then sending it off. The pitcher maintains a component of force on the ball of constant magnitude of 30 newtons, always in the direction of motion. So she's pushing always tangent to the path. So even though the path is a circle, when you do your FD cosine theta, what they're trying to tell you is that the force and the instantaneous displacement are in the same direction. So we're talking about cosine of 0. Okay, and the speed of the ball at the top of the circle is 15 meters per second. And we want to find the speed at the bottom of the circle. All right, so I would suggest if you came here because you're like, I don't even know what's going on, pause the video right now and see if that's enough to do TME at A plus the work done by her equals TME at B to find the speed at B. And again, really try to do it yourself if you can. Okay, so try to have enough room here right neatly. So we have TME at A plus she's an outside force. That's why I like doing the system problems first, right? You can imagine the ball is our system and she's outside of the system. So TME plus the work done by the pitcher equals TME at B. So this ball is going to have more energy than if we just dropped it and there were no outside forces. All right, so we need to set sea level. So let's call point B sea level. And I recommend, there's clearly no springs here, so let's not add that term. We just have mg, oops, plus work. Okay, I fixed that, plus the work done by the pitcher. So is the ball above sea level at A? Absolutely. So it's, and the mass doesn't cancel, right? Because the work is not a function of the mass. So even though it looks, it's in all the other terms. So 0.25 times 9.8 plus the height is 2 radii, or 1.2. Plus, often things start at rest, but in the windup, right, she's already given it some speed. And we know that is 15. Plus her force, which is 30 newtons, so that's pretty easy. And the distance through which she acted, which is half of a circumference times cosine of 0, because her force was with the motion, and cosine of 0 is 1. I'm running out of space. Okay, so I just did the left-hand side. That's going to equal mgh at B. Luckily, I'll do this a different color so you can see what's going on. That's 0 because it's at sea level. What we decided was sea level. Plus, and this is what we're looking for, plus 0.25 times V at B squared. Okay, that's the physics, not forgetting that that there is a change in height, even though she's touching it the whole time. Okay, so I'm going to pause the video, crunch the numbers, and then we'll compare notes. All right, so I'll talk you through what I did while you were gone. So I did plug in the numbers just in case you want to check your work. Her force times half the circumference is her force times the 2 cancels times pi r, and that was 56.52. Okay, so this is the initial GPE, gravitational potential energy. This is the initial kinetic energy. this is how much work she did by exerting a force through distance, and this is what we're looking for at the end. All right, and I was curious to know she put more energy in than the ball already had. And then you reduce and solve for the speed at B, and you get 26.5 meters per second. All right, so the trickiest part of this, I think, was just understanding what the heck the problem was asking for, and, realizing that the distance was half of the circumference. All right, this is 23, but we don't know this yet, so I'm going to cross this out. I'm going to Photoshop that out. All right, so we have a toy cannon. So like a, I don't know, Nerf gun or whatever. Anyway, there's a spring to project, and you got to be careful here because they're trying to be realistic. But that means the mass is in grams, right? It's a Nerf thingy. So it's 5.3 times 10 to the minus 3 kilograms. The spring is originally compressed by, again, got to convert, by 5 centimeters. So this is where the spring wants to be. And the delta X initial is 0.05 meters. And it has a force constant of 8 newtons per meter. So that's going to help us find the spring stored energy. We don't need to convert, thank goodness. Okay, when the cannon is fired, the ball moves. So what's interesting, again, I'm probably realistic, the spring is done pushing, but the barrel of the gun goes on for a little bit longer, right? Because you don't want the spring kind of popping out. So the total distance traveled is 0.15 meters. So again, I think this is realistic, that the spring force acts for only 0.05 meters, but friction acts for a different distance, right? The forces might not all act for the same distance. So let's see, let's make friction, there's your force of friction. Okay, and then we want to know the speed at point B. So we're going from point A to point B. And so we're talking about energy, not forces, even though there is a force there, right? This is really an energy problem. All right, so that's everything that's going on. So we have TME at A plus technically, you might want to get in the habit of saying it's the sum of all of the work done by all of the external forces. You may have more than one. And that's going to equal the TME at B. All right, so sea level is this red line. So there's no change in sea level. So you don't have to worry about gravitational stored energy. So at A, the spring is not at the dash line. So the spring is storing energy. And what happens between A and B is friction does work. And at point B, the spring has given away all of its energy. So even though the ball is not at the dash line, usually so the ball is no longer at the dash line, but the spring has returned to its original length. Okay. And so that equals just the kinetic energy at B. All right, so let's plug in what we know. 1/2 8 times 0.05 squared. So our original energy, plus, we don't have to calculate friction, so that's nice. The force times the distance of the displacement, and that the friction worked for 1.15 meters. And then the angle's tricky because it's not necessarily an angle on the diagram like it was for inclines. This is our force. That's technically it's the displacement, but and it's a dot product, but if you don't know what that means, that's okay. That's the force, that's the velocity. What is the angle between these two? Cosine 180. And that's always going to be true for kinetic friction. I just want you to see where it comes from. Okay, equals 1/2 m, but because m is so light, we're going to get hopefully a significant speed. Sorry, I'm running out of space. Times v at b squared. Okay, so sorry, that ran out of a little bit of space, but hopefully you can follow along. Okay, so again, this is a Nerf ball kind of thing. So the spring only had 1/100 of a joule. Friction did not take away much energy because force was so small. And so even though there's not a whole lot of energy to go around, the mass is so small that it still ends up with a speed at 1.4 meters per second, which is not very fast. It's a pretty safe Nerf gun. That's like 3.15 miles an hour. Okay, and then I'll try to remember to put B. You will know how to do B and C after we do bungee jumps. So I'll add that homework when it has more meaning. All right, so hopefully that went well. Springs and friction together. Okay, so there's a lot going on in this question, but it's a good question and it helps you practice organizing a whole bunch of information. All right, so we have the boy in the wheelchair, and you have his mass, 47 kilograms, and he beats the skateboarder who doesn't get to be even in the picture because he lost. Okay, so the boy has a speed of 1.4 meters per second at point A, so he's got kinetic energy at point A, at the top of a slope, and they give you the height of the slope because you need to know how high you are above sea level. And you also have the length of the slope because you need to know the distance through which he traveled to calculate the work done. And at the bottom of the slope, otherwise known as point B, his speed is 6.2. So he also has kinetic energy at the bottom. Assume air resistance and rolling resistance can be modeled as a constant frictional force of 41 newtons. Okay, so again, they're trying to be realistic and say, like, he's running into air molecules and there's energy loss due to, surfaces rubbing together. Let's just call that 41 newtons on average so we can do this problem. And then it says find the work he did. So that's the hint that he is an outside force. And tell me if you want to talk about this in class. Because I don't want to muck up the video, as my brother-in-law says. Even though he is part of the system, he's pushing, he's pushing on the tires, making the tires go forward. The tires are pushing against the ground, blah, blah, blah. It's complicated. Just pretend like we're just doing a problem where his force is with the motion. He's clearly forcing the environment to work in the direction of motion. I just realized talking that through, that is kind of tricky. So, but I like this question is because we're going to have the TME at point A, which is not going to be super challenging, plus the sum of the work done equals TME at B. So you should be old hat at TME at A at TME at B. What's tricky here is that there could be multiple forces doing work. All right, so let's just talk this through. And again, no spring, so we don't need to worry about that. Is he above sea level at A? Yes, we're going to have that term. Is he moving at point A? Yes, we're going to have that term. Okay, there's a normal force, but it's perpendicular to the motion. There is weight, and it is an external force because the Earth is not part of the system, but the work done by gravity is included in this MGH, And I think we're going to talk about that separately. So again, please reach out during class if you want to talk about this. But we're actually saying, actually, my bad. We are actually saying the Earth is part of the system. We're just not drawing it. So this energy is part of our system. Okay, so the Earth is a force, but it's an internal force. We just are not drawing the Earth and showing that those two forces cancel. All right, hopefully that wasn't too confusing. So he has MGH. He is moving. The normal doesn't do any work. That's velocity, not a force. And we want the work that he did. So I'm not going to say FD cosine theta. I'm going to say work done by the boy plus work done by friction. Oh my goodness, I'm running out. I keep drawing the picture and then running out of space. Equals TME at B. Okay, at point B, he's essentially at sea level, so he has no MGH, but he is absolutely moving, and we know everything about how fast he's moving. Okay, so make sure you know that's all one line. All right, let's plug in what we know. So we know, let's do purple. MGH is going to be 47 times 9.8. That's why they told you the 2.6, is because you need to know how high he is above sea level. Plus, somewhere at some point, he or a friend or a jetpack or something gave him some kinetic energy. Plus, we want to know what additional work he did. Plus FD cosine theta for friction equals 1/2 47 times, dang, I still run out of space, 6.2 squared. Okay. So he had 1198 joules of kinetic energy. He had 46.1 joules of, did I say, this is potential, that's kinetic, plus the work done by him, that's what we're looking for, plus 41 newtons of total resistive forces times the 12.4. Okay, so there's two different distances. One is for height above sea level, one is for the actual distance traveled. So be careful that you know when to use which distance. And since it's, sliding friction and air resistance opposite the motion, that's going to be cos 180. Equals, at the bottom, he has 903.34 joules. Sorry, that's messy. 903.34 joules. Okay, let's combine numbers here. Okay, pause. All right, so not sure where I left off, but I'll try to go through this quickly. So his initial energy was 1244 joules. Friction took away 508. So even if he didn't do any work, if he, didn't push hard on the wheels to move him forward, he would have ended up at the bottom of the ramp with some speed. But I guess he's in a race with a skateboarder. So he just, if you want to check your work, got this number, got that number, solving for work of the boy, he put an additional 167 joules of energy, 168 rounding joules of energy into the system. So friction took away more than he put in. Not that we care, but I'm just trying to give you some reference of why you would want to spell these things out separately. Okay, so the one thing I want to say in terms of problem solving, and then we're done, is that sometimes people find this challenging because you're, like, when it says find the work done, people want to go sometimes just plug and chug into, oh, I know, we have a formula for work. Work is FD cosine theta. And then they're like, I don't know the force of the boy, even though I know the distance is 12.4. So you're calculating what he did by inference. You're saying, okay, I don't know his force. I do know the distance, but I don't know the force, but I know what happened. I know that he ended up with this much energy. So again, if you want to think money just because it's concrete, um, you know, the with there was 12,000, there was $1,244. He spent 508, but he still ended up with 903.34. So he must have earned some money as well, right? So you can just say, all right, this is my bank statement. I know I wrote this check for 508. This is my new bank balance. So what did he have to do? He had to put some positive money in, and this is how much money he had to put in. Okay, so, just be really flexible. Sometimes you care about the speed. Sometimes you want to leave it as kinetic energy. Sometimes you care about the forces individually and you're going to do FD cosine theta, or maybe the distance through, like if you're a volleyball spiker, through what distance did you remain in contact with the volleyball to get the job done? But sometimes you just want to know, hey, how much energy did I put into the system? Just leave it as work. All right, so I think that's my recollection of what people find the most challenging. All right, we will get a little bit more practice with work. Hopefully the energy part, like the TME parts, find it is feeling better. But thinking about adding that extra work term is the new content. So thank you for listening, and I'll see you in class.